So welcome everyone to the Cryptanalysis and Symmetric-Key Primitives session. The first talk is entitled Multiple Tweak Differential Attack Against Scarf. It's a joint work with Christina Boura, Sharam Razulzadeh, Dimansa, and Yosuke Todo, and Yosuke will give the talk.
Thank you very much for the introduction. So I'd like to talk about multiple tweak differential attack against scarf. And this is a joint work with Christina, Shaham, Diman, and Yosuke present the talk. Okay, so first of all, this is a more overview of my talk. The focus of our research is a new type of block ciphers which was designed for a specific purpose. So for example, so the scarf, this is our main focus in this talk. So scarf is designed for cache attack protections. So contention-based cache attack protections. And this type cipher is very unique. So the block length is only 10 bits and tweak length is a 48 bit. And also another example is a BIP. So this is designed for memory safety. And block length is a 24 bit and the tweak length is a 40 bit. So this type of cipher is very unique because block length is very, very short. So actually this type of cipher is only designed for the specific purpose. So we cannot use this cipher for general purpose, satisfying confidentiality, for example. But in this specific purpose, so this type of short block length is very suited. And also, of course, the block length is too short, then we need to tweak. Otherwise, so the input is too short. So we need to tweak. And in that case, the tweak length is extremely higher than block length. But now we have a question. So usually, when we analyze the block cipher, we should evaluate the security against a traditional attack, traditional statistical attack, such as the differential attack and linear attack, because these two attacks are main attacks against the block cipher. But the question is, such a traditional analysis is enough or not for this type of cipher? So our conclusion is a more careful analysis is required. So now our target is the scarf. So we propose a practical precious differential probability evaluation for scarf, and also provide a 7-round key recovery attack and full-round multi-key distinguisher. Okay, so differential cryptanalysis. So alpha and beta is the input and output differences, and expected differential probability is computed by this equation. So if EDP is very close to the 2 to the minus n is the block length, then we can, it's a very difficult to attack. So, but if EDP is very higher than 2 to the minus n, so we can distinguish the cipher with query complexity of the inverse of the EDP. But new type of ciphers, so they're very short block lengths. So in that case, so they're only guaranteeing 2 to the minus n differential probability is enough or not. So this answer is no, because we have tweak. And what happens? So of course, in that case, the EDP should be computed by this equation. So we additionally activate the tweak, and we should divide it by the size of the tweak. In that case, we can collect more data than 2 to the n. So the ideal probability is 1 over 2 to the n minus 1. And then we observe the bias like linear cryptanalysis from the ideal probability. So in that case, the EDP is this equation, 1 over 2 to the n minus 1 plus epsilon. So assuming the binomial distribution, we can distinguish with a query complexity of epsilon squared epsilon over 2 to the n minus 1. So of course, so this value is larger than 2 to the n. So normal block cipher is of course beyond the data complexity, but in this case it's possible because we can activate the tweak. Okay, so now the target is a scarf. So scarf is a 10-bit block and 48-bit tweak and 80-bit security. And so, sorry, this is a round functions and the light is over so the encryptions, four encryptions. So SCAF has two security requirements. The one security requirement one is a so-called collision model. So attacker can query xt and x prime t prime, and if the output is the same, the oracle return 1, otherwise oracle return 0. So the requirement is the attacker can't distinguish the cipher up to the 40 query and to the 80 time. And another security requirement is so-called enc then dec. In this case, attacker can query x, t, t prime, and attacker can run the corresponding x prime with one query. So actually, we should compare these two models. So the security requirement one collision model is a weaker security. So it means more difficult to break. So, so security requirement one respects the real adversary scenario for cache attack. So in the case of the cache attack, we can query the index tag, and if correct, we can observe the correcting case by observing the time difference. But so in practice, so security requirement 2 is a much stronger security. But of course, in this case, there is no such oracle in real world. So, but security requirement 2 is much familiar with cryptographers because usually cryptanalysts use this assumption. Okay, so now we want to discuss the differential property of SCAF. And so the first we focus on the G function. So the G function is, can I go back? Yeah. G function is this F function cell in like a facial structure. Okay, so now if we ignore the last AND gate, G function is key-dependent linear function. And also we have very unique feature of the G function. So G function EDP is always at 2 to the minus 5 if alpha is non-zero, independent of the output difference. So even if the output difference is a 0. So now we can exploit these features, and we next analyze the round function. So in this case, we also use the same feature. So now EDP alpha to the beta is PS alpha L beta R. This is the differential probability for S box times 2 to the minus 5 if alpha L is non-zero. So it means this probability is independent of beta L. So beta L is the output left side difference. So any beta L appear with an equal probability, and PS is a differential probability. Okay, so next, so that we add arbitrary permutations, so the F after this round function, what happened? So in that case, so the EDP is computed by the EDP from the EDP for round functions times EDP for the any permutation F, and sum over the intermediate difference gamma. So in that case, we also have the same property. So the EDP does not depend on alpha R if alpha L is non-zero. So finally, so in SCAF is a very unique feature. So the enc then dec structure. So this is the last round of SCAF, and the last round enc then dec structure. So the 1 round plus 1 round. So and we can also analyze the differential property. So unique feature is in the case of the alpha L is a non-zero. In this case, so that we have differential probability from alpha L to beta L is a special unique S box of the S of S inverse. Okay, so now we can analyze the differential property for each component of the SCAF, and then so that we extend this differential probability by adding the round function, and finally we get the full expected differential probability matrix. Okay, so now, to compute the EDP accurately, usually we need order 2 to the 3n time in general. But in the case of SCAF, thanks to the G functions, and the G function, the outputs the arbitrary difference with the equal probability. So by exploiting this property, we can evaluate the all EDP by only analyzing these 4 patterns. And in that case, the time complexity is reduced to order 2 to the 1.5n. Okay, so now we have full EDP for the SCAF. Then how to get the best distinguisher? So the strategy is a multiple differential. So usually, we use only one input difference and one output difference, and we exploit this differential probability. But in the case of SCAF, the block length is too short. It's not so difficult to exploit all kinds of the input and output differences. So in that case, we have a multiple differential attack. So when we use LLR statistics, the data complexity is about the inverse of the capacity, and the capacity is computed by this pattern. The top pattern is we use all non-zero input difference and all non-zero output difference. But this is a phase-like structure, so only right-hand active is enough. So almost very close. She is almost close to she. Or and for the key recovery efficiency, so the last C is enough in general. Okay, so this is a summary. So actually, by using the developed tool, we measure the capacity for the reduced round and to full round SCAF. So we get this result. And to confirm our estimation, so we also provide experiments. And this is a 4 plus 4, and this is a 5 plus 5. And so the experiment follows the theoretical results. So our theoretical estimation is justified by experiment. Okay, so now we want to show the key recovery attack against 7 round. So first we should define the proper 7 round SCAF. So the original SCAF has 8 rounds. Then we have the round function here. But now for the reduced round, we skip round functions for the only initial round function. But the tricky schedule, we use the original one. So attack consists of 3 parts. So the first we have data collection, and next the partial key recovery using 6 plus 6 round multiple differential. And the final part is key recovery using the differential distinguisher. Okay, so data collection. So first, we prepare the 2 to the 30 tweaks TI, and next, so we create the full code book to each T0 TI. So it means that we first ask the full code book here, and we get the full code book for this part. So in that case, it's very nice, unique feature. So if we have TI and TJ, and full code book here, then we also get this line because this is equal. So by using this property, so we can correct 2 to the 29 plus 29 plus 9 pairs to the 67 independent pairs in total by using the data limitation, even if we use the data limitation. Okay, so next is the multiple differential distinguisher. So we add 1 round key recovery and use the 6 plus 6 multiple differential. So in that case, right side alpha and the right side beta is arbitrary difference. And in that case, the capacity is to the minus 60.89. Then it's enough to recover the gate 30 bit of K1. But K1 has a 60 bit in total. So this procedure only recovers half 30 bit key. So remaining 30 bit is not recovered by using this procedure. So to recover this part, so we next reduce the distinguisher round and we extend the key recovery round, only the G function. Then we use differential distinguishers from 0, 1 to 0, 1. So in that case, we can recover the remaining 30 bit of K1 and the 5 bit of K2. So in this case, we already recovered this K1, and it's not so difficult to recover the K2, K3, K4 by external cryptanalysis. Okay, so next is the merge key full-round distinguisher. So actually, the initial motivation is the definition of bit security. So actually, it's a very interesting existing work. So the Asiacrypt and WY21, WY23 is the Asiacrypt papers. So these papers discuss how to define bit security properly. So this is the case of the MW80 papers. So this is the definition. TA with the time complexity, then the bit security should be defined like this equation. It's very interesting because if we assume this definition is correct, then the scarf, bit security of scarf is, we compute it. So in that case, only 67.55. Of course, the bit scarf provides 80-bit security, so it's lower than 80. So it means scarf doesn't provide the 80-bit security or not. So this is our initial question. So actually, unfortunately, the MW80 paper doesn't provide concrete attack procedure. But WY21 and WY23 papers focus on the concrete attack procedures matching to the bit security. So, but we check these papers, so the attack procedures repeat the algorithm multiple times and store each bias and combine everything. So usually in the symmetric key cryptography, so that this is regarded as a so-called merge key setting. So attacker can rekey their block ciphers and observe the bias and several times, and finally combine everything and distinguish. So of course, in this case, by using the algorithm of the WY23, so we can distinguish the scarf with the ideal permutation. But of course, it's a merge key setting. So in that case, for both SR1 and SR2, the complexity is lower than 2 to the 80. Okay, so finally, I want to discuss the observations about the additional observation. Okay, so first observation is the connection to the boomerang connecting table. So actually, when we analyze the differential property for scarf, so the unique feature is the last round, so the 1 + 1 round structure. Here, we have we need to evaluate the DDT of S key additions and S inverse. So actually, this differential distribution table is highly related to the boomerang connection table. So if boomerang connection probability is high, then this differential probability is also high. So it's very highly related. So actually, if BCT is higher, then the 1 + 1 differential probability is higher. So up to 3 + 3 rounds, so the BCT strongly affects the differential probability, but from 4 rounds, differential probability is more influential. But yeah, in this structure, the BCT is very important. And finally, we want to find a better S-box. So actually, if we replace the scarf S-box with the APN, then we know the differential probability is much lower. But of course, the APN is not so low-latency. So scarf S-box is designed for low-latency. Scarf S-box is chosen from the low-latency S-box candidates. And we explore these these S-boxes satisfying the same design criteria of the scarf. And finally, we found, and we execute our differential evaluation algorithms for these S-boxes exhaustively, and we found this alternative is much lower differential probability. So it's a much nice alternation. Okay, so I want to conclude my talk. So recently, so that we have block cipher with very, very short block lengths. So in this case, so usually we use the differential probability. So by using, for example, MIRP or SAT or several tools, and we can estimate the rough differential probability. But however, so in this case, so guaranteeing the 2 to the minus n probability is not enough. So we need to know 2 to the minus n plus epsilon, and we need to know this epsilon. So in that case, so estimating the EDP is required. And so in general, it's very difficult, but thanks to the property of the G function, it's very efficient in the case of SCAF. And we apply this idea, and we estimate the differential probability accurately, and then apply the attack the SCAF, and I show the 7-round key recovery attack and full round multi-key distinguisher. And finally, the observation is original SCAF S-box is not optimal in the context of the differential cryptanalysis, so that we have another much better S-box. Yay, that's all. Thanks very much. Oh.
Thank you, Yosuke.
Long press.
Long press, that is great. Thank you, Yosuke, for the nice talk. Is there any question?
So what you said there, that if you have an output of a given number of bits, guaranteed 2 minus n is not enough. It resonates very well with some work I've completed recently with a student. We have analyzed the PAC version of Karma, where you just output a few bits, sometimes as little as 3. And one could have intuition, well, if the likelihood is very small, then you can't use it. And in fact, yes, you can use it up to 2 to minus 40, even if you're outputting just 3 or 4 bits. And one might think, oh, 2 to minus 8 as a limit. So it is a fact that what you have there is essentially a bias. And we already know that from linear cryptanalysis, that a small difference from the noise can still be used.
Yeah.
And I've seen quite a few papers around that were assuming, well, if this bias is small, you can't use it. But actually you do. And so I thank you for remarking this, because I've seen these omitted several times. Yeah, so it's an important observation.
Yeah, thank you very much for the comment.
I have a question related to that. Actually, is it not about the data collection algorithm you provided, which was not observed by the designer of SCARF, and which allow you to have much more pairs than what you should have in theory?
So in in this part?
Yes, exactly. I think this is because the designer did not notice this.
So the designer also used this structure by estimating the differential probability experimentally. So, but so they don't show the how to use this property in the concrete attack. So in this case, it's a bit different.
And one last question, would it make sense to use the quasi-differential framework to study precisely the probability of the differential of the ETP?
Could be. Yeah.
Okay. Yeah. Any other question? No? So thanks, Yosuke, again. So the next talk is Ultrametric Integral Cryptanalysis by Tim Baines and Michel Verbowed. And Michel will give the talk.
mic working? Okay, seems like it. So yeah, thank you, Patrick, for the introduction. So I will indeed be talking about ultrametric integral cryptanalysis. But before I get into that, I would like to explain a bit what integral cryptanalysis is and why it is interesting to make it ultrametric. So integral cryptanalysis was originally kind of named and described by Knudsen and Wagner. And the idea there is that you kind of try to exploit the structure of your cipher to get some specific properties. So they formulate that if you take some input set and you, which has as a structure that you saturate, or so you take all possible values over a part of a state and keep the rest constant. So in this case, for AES, for example, that would be activating a single S-box. You can then propagate information about the state forward, and eventually what you get is that at some point you can't really say much anymore, but you end up with this kind of zero-sum property. So every output bit sums to 0 over this input set. Now, these kind of properties are not really unique to integral cryptanalysis itself, because much earlier, higher order differentials were introduced, and there you kind of exploit that if the degree of your function is small, you can take some affine subspace of a dimension higher than this degree to also get a similar zero-sum property. And then later on, with recent work, or relatively recent work by Todo, which introduced the division property, these two kind of approaches have emerged. And the idea there mostly is that you, again, construct such a input set, which is a specific structure, and then you keep information about which functions on this set sum to 0 and which don't. And eventually you end up at the end that only linear functions sum to 0, and so you get these zero-sum properties. This has then been generalized with parity sets, and there has also been like a method that is closer to the algebraic approach called monomial trails, where you work backwards and try to predict the coefficients in the algebraic normal form. And then in recent work, we showed that these two things are dual, so you basically get the same results. Now, this recent line of work has one kind of problem, and that is that it's defined over F2. So the only things we can find are these zero-sum properties over F2. However, in the original description of integral cryptanalysis, we had like, not at the end, but in the middle, we still had these saturation properties, where we could see that for a single bit, it would be 1 exactly half of the time. And then between that, you can also maybe have some properties which have higher divisibility. So they're not just even, just some divisible by some higher power of 2, but are not quite saturation. And so to start this work, we did some experiments on present. So we took the 4-round distinguisher by Bourrat and Canto, and then we checked for each output bit how often for a set of random keys we would get, so we would count the number of times we get 1. And as you can see for this example, only even values are present, but what we can also see is that all the values are actually divisible by 4. So in this work, our goal was kind of to analyze and understand these divisibility properties and use this to improve our understanding of integral cryptanalysis. And the way we did this is we basically cooked up a new cryptanalytic method within the geometric approach. And for this, we had to introduce 2 new ingredients. One of them is a 2-adic absolute value on the rationals, and the second one is a change of basis, which represents kind of a multiplicative analog to linear cryptanalysis. So for this work, so in the rest of this presentation, I will first introduce the geometric approach and how it works. Then I will introduce the different ingredients, and then I will put everything together, and then we can do some cryptanalysis. So first of all, the geometric approach. The idea here is that we extend our primitive that we try to analyze linearly to a function on the kind of free vector space on its domain. So that means we kind of assign weights to every possible input value, and then we can propagate this vector of weights through the cipher. And this is just a linear operation. And to describe a cryptanalytic property, we can then take a linear function of this propagated vector and then get a single value in a field which we can use to distinguish our cipher in some way. And so this linear operator, its matrix representation, we call it the transition matrix, and it has some interesting properties. First of all, the multiplication of transition matrices of two functions gives you the composition of these, the transition matrix of the composition of these functions, and similarly a tensor product would result in the transition matrix of parallel application of these functions. Then you can also take the dual operator of this function, so you can directly operate on the dual space, so the space of linear functions on a free vector space, and propagate this backwards, and then evaluate it on some weight vector at the input. And this is kind of important to distinguish, because we will have different bases at some point for these two different spaces. So how would we then use the geometric approach to actually get some cryptanalytic method? So as an example of a cryptanalytic method that is already described in the geometric approach, I have linear cryptanalysis. And the idea now is that we take some, so we use some kind of basis for our two spaces, which simplifies some important component of our cipher. And since most ciphers have a key addition, it might be interesting to simplify the translation operation. And so if we look at these transition matrices, they form basically a group action on a free vector space. So with that, we can use kind of the representation theory of groups to get a basis of characters for the dual space we were looking at. And then due to duality of bases, we can then also find the basis on a free vector space. And so if you then take this change of basis of the transition matrix and you look at that, you get the correlation matrix. And as a little example, I wrote down how you would compute this for the key addition with a single bit. So when you do this change of basis transformation, a lot of properties from the transition matrix carry over. So you get again the product of correlation matrices, which is the correlation matrix of a composition, something similar for parallel application of functions. And then also, any linear map has a really simple representation as a correlation matrix. The details are not that important, but this, for example, gives rise to the usual kind of propagation rules for linear trails to a cipher through XOR and copy functions. This alone, however, is not really enough to find a cryptanalytic property that you can use. You would also try to, you actually still have to find it. With linear cryptanalysis, it happens that we can try to compute the correlation of linear approximations over our cipher. And the way we usually go about this is we use this property that we can decompose our primitive into round functions, and so we can decompose our matrix into a product of simpler matrices. If we then want to evaluate a single linear approximation or its correlation, that would correspond to a single coordinate in this matrix, and we can then do a further decomposition into the sum of trails, or the correlation of these trails. And so the correlation of a trail is basically the product of individual coordinates from each of these matrices. Now, because we did this change of basis, and it's also kind of bitwise defined, we expect there to be some set of dominant trails which dominate kind of all the other trails that are left over. So if we then kind of assume that these leftover trails are zero, we get a really good approximation of the actual correlation of our linear approximation. On the other hand, we can also kind of try to not use this assumption that the non-dominant trails sum to zero, using zero correlation linear cryptanalysis. There we can actually prove that if all the trails are zero, then we also expect the correlation of our approximation to be zero. And we can then exploit this. Go. Okay, with that we can get to our first new ingredient, and that is the two-headed absolute value. So with the two-headed absolute value, the goal is to express our divisibility properties neatly. So if we have a cryptanalytic property, like an integral property would have this vector u be some indicator vector of your input set, and this vector v would then, or this function v, would map a single output bit to the rationals. And if we then evaluate a property, we expect to get 0 modulo some power of 2. And the way we would then neatly kind of describe this is with the two-headed absolute value. So over the integers, the two-headed absolute value is defined as 1 divided by the largest power of 2 that divides the integer. And then you can extend this to the rationals. And the idea then is, since 0 modulo some power of 2 means that the actual value should be divisible by this power of 2, we get a bound on the two-headed absolute value of our property. Additionally, and that's where the name of the paper comes from, there is this ultrametric triangle inequality which holds for this absolute value, which is significantly stronger than the normal triangle inequality. Okay, and then for the second ingredient, we have this multiplicative analog that we want to do. So we start with the same setup as with linear cryptanalysis, but in this case, we want to diagonalize something else. And what we chose is we want to diagonalize multiplication of bitwise ends. It turns out that if we look at these transition matrices and this bitwise end, we don't get a group, but we still have enough structure that we can use representation theory to find kind of a basis for our dual space. So, and this basis then corresponds to basically just the monomials as we're used to them, but then lifted to the rationals. And then if we take so this is for the dual space, and then if we try to find the basis in the free vector space, it becomes a bit complicated, but it's still viable. So now if we take this change of basis, we get the ultrametric integral transition matrix. And additionally in the paper, we show that if we then take this matrix modulo 2, we get the algebraic transition matrix, which we used in an earlier work to kind of develop integral cryptanalysis. So in that way, this basis kind of lifts integral cryptanalysis out of F2 into the rationals or into the two-headed numbers. So this ultrametric integral cryptanalysis transition matrix, we expect this also to lift, not to lift, to also have the similar properties to the correlation matrix, as you can see here, but that's easy to fix, to something that's correct. So we get the product of matrices again for the composition. For parallel applications, we get the tensor product. And then we get that so-called multiplicative functions, which basically homomorphisms of the bitwise end, that they will have a very simple structure. And so the details are again not that important, but we do get simple propagation rules for specific components. Like for the AND gate, takes now the role of the XOR in linear cryptanalysis, and there is also a propagation rule for copying. So with all these properties, we expect that we can kind of do, or we can do a dominant trail approximation again to try and find these divisibility properties. And so in this case, instead of using the ordinary absolute value, like earlier, to find dominant and non-dominant trails, or to separate them at least, we will be using the two-headed absolute value. And here, this ultrametric triangle inequality comes into play, because now we don't have to assume that this kind of error term is small, but we can actually prove it by just proving that every trail in this error term is small. And then we can take the kind of the maximum over all the trails due to the triangle inequality, and then get a bound on their divisibility. And that then kind of results on top in a property modulo some power of 2. So we can now go back to the property we kind of observed earlier. And so the idea there is that we can now try to use this dominant trail approximation to prove that our property is actually correct, or that this actually holds. So we had this divisibility derived for, so we now want to prove that the correlation of all possible trails for our property is 1/4. To do that, we define our property in our ultrametric basis. For the output, that's really simple. We just looked at a single bit, so this corresponds to one of the lifted monomials. However, at the input, it becomes a bit more complicated, because what we do is we take a set that takes all possible values on this rightmost S-box. But this is not, cannot be expressed with a single basis element in our ultrametric basis, so we kind of have to add some extra stuff. Yeah, you can read in the paper what the exact details are there. But so what we can do then is, so this is kind of a quick overview. What we do then is we do an approximate miss in the middle approach to prove that all these trails are small. So similar to linear cryptanalysis, where we would start from the top of the cipher and propagate all possible masks for non-zero trails forwards, and then we can also start from the back and propagate non-zero trails backwards. In linear cryptanalysis, you would then prove that the intersection is 0, so that there are no non-zero trails. But in our case, what we do is we show that somewhere here in this lower right super S-box, you get at the intersection of trails that the correlation will always be small. So the correlation will always be 1/4. Again, like more details about how this works can be found in the paper. Now, so this was a simple example. It was just 4 rounds present, but it gets a lot more complicated and takes a lot more work to do this cryptanalysis by hand for a higher number of rounds and also for more complex ciphers. So we also implemented a set-based tool to automatically find the divisibility of integral properties. And we then applied it to the integral properties that were found before in the literature on present and Simon. And what we see is that in many cases, especially for the kind of older properties, we see that we get really high, we actually see these higher divisibility properties. And this can go as high as, so this is log 2, so this can go as high as divisibility by 512. However, we also have a more negative result for the really optimized properties. So they have like minimal data for a specific number of rounds. We sadly don't see like any improvements. However, in general, we still expect that key recovery attacks will be able to use this higher divisibility to filter on the key more efficiently and thus require less data. And with that, I've come at the end of my presentation. So I will leave you with this kind of short summary of what ultrametric integral cryptanalysis is and how it compares to linear cryptanalysis.
Thank you for the talk. Is there any question? So I have some questions. First, what did you implement exactly? So you first rely on another tool to search for integral property, and then you apply your tool to search for the division property, not really the division property, but the
so this divisibility. Yeah, so that's what we did. Okay. So we rely on a tool that can actually find properties modulo 2, and then we check if it can go higher. But in the end, if you can always kind of modify the models we have to just first find properties modulo 2 and then check with higher divisibility. So
and how efficient is it, for instance, on present?
So so we didn't optimize it completely, but like a couple of seconds, maybe a minute at most for the most complex things.
And so the question I asked you earlier, so what about the multiple of 8 property of AES? Is it related to this? How we can apply this framework to find it
Yeah, so
possible?
So the multiple of 8 property is kind of, on AES, for example, is defined on like pairs. So it doesn't really we can't directly apply ultrametric cryptanalysis, but I think we can, we might be able to describe it by taking the same kind of ID. So we would need a different basis in which it is easy to kind of describe a property, and then we can use the two-headed absolute value to do a dominant tail approximation and prove that the property is kind of divisibility by 8.
How do you handle a linear layer with this framework? Is it easy, or do you have to consider them as S-boxes?
Yeah, so the linear layer, so I've written this down here. Like, ultrametric integral cryptanalysis kind of switches the roles of how we normally see S-boxes and linear layers. So in this case, the linear layers kind of provide confusion for a trail-based approach, and the non-linear layers are really easy. So we need to either describe them as S-boxes, which for like AES is not really possible, but for some things it is. Or we do a decomposition in copies, XORs, in copies and XORs, basically.
Okay, thank you. Any other question?
Thank you very much. So can you go back one slide? Yeah. So you say, sorry, the no improvement of minimum data properties means you cannot improve the round, and in the context of the data complexity, in the same data complexity, it is okay. So my question is, you say the reduced data complexity in key recovery attack. So do you find concrete such an example in the application?
So we tried a little bit, and so we worked out an example on like 6 rounds present, where we reduced the data complexity because we could just filter more keys, so we needed less properties in general. So in this case, we used a really low data property, and then we noticed like, okay, we have this higher divisibility, so that means we need to sample this single property less times. So lower data.
In this case, the number round is much reduced, so then the best.
Yeah.
Okay.
Yeah, that's cool.
Okay, thank you.
Thank you again. The next speaker is online, right? Yes, it's online. So the last talk of this session is generic differential key recovery attacks and beyond. I don't know. Okay, 1 second.
Can you hear me? Can you hear me? Can you hear me?
Hi. Are you ready?
Oh, yes.
Yes, okay. Can you put your presentation in full screen?
Oh, can you hear me?
We can see it, but I think you can put it like in full screen. Yeah.
Okay.
No. Okay, let's go.
Oh, okay.
This talk is generic differential key recovery attacks and beyond. It's a joint work with Ling Song, Wuming Liu, Qingyang Yang, Yinsen Chen, Lei Yu, Jing Wang, and Yumin will give the talk. You can start.
Okay. Hello, everyone. Now I will give the presentation about our work, generic differential key recovery attacks and beyond. There are 5 parts of our work. It's shown in the outline. In the first part, I will introduce some basic knowledge. As we all know, differential attack was introduced by Beham and Shamir in 19...
There is a problem here. Can you wait for 5 seconds? It's okay? Okay. Sorry, you can, I think you can start again. Thank you. Sorry.
Start. Can I start?
Yes, you can start. Thank you.
I will give the presentation about our work, generic differential key recovery attacks and beyond. There are 5 parts of our work. It's shown in the outline. In the first part, I will introduce some basic knowledge. As we all know, differential attack was introduced by Beham and Shamir in 1990. The attack is divided into 2 parts, the distinguisher and the key recovery. The first step is to find a high probability differential, delta x, delta y, covering a large number of rounds. The probability of differential should be higher than 2 to the minus n, where n is the block size, with the increasing of rounds. This target is hard to achieve most of the time, so the boomerang attack came out. It connects 2 short differential of high probability to construct a long differential trio. However, it's unadopted children plaintext ciphertext attack, which is a limitation. So we have the children plaintext variant of boomerang attack, the rectangle attack. It considers the difference in the middle as accurately as possible. In many situations, the rectangle is more common for key recovery attacks. Once the high probability distinguisher is found, we can extend some rounds in the backward and forward directions of the distinguisher with probability 1 to mount key recovery. In recent years, many improvements have been proposed for the key recovery, as shown here. The structures of data, it allows to enjoy the birthday effect and potentially attack more rounds without increasing the data complexity and the probabilistic extension. As shown in this figure, the probabilistic extension is used in the mixed column operation of the rounds R+1. Among the techniques for key recovery, the key guessing strategy has received considerable attention. For example, the order of guessing key information and the flexible key guessing strategy. In the second part, I will introduce 2 key recovery attacks, the generic classical rectangle attack and the basic differential meeting in the middle attack. For convenience, I will call them GCRA and BDMA. As for GCRA, it allows to guess some key bits, KB prime union KF prime, before any quartets are generated. The corresponding key recovery attack, as shown in this figure. We can guess a part of, or take the forward extension as an example. We extend the differential with probability 1, and there are RF active bits. The involved K bits are KF. We can guess the KB prime K to determine the difference in the EF part and obtain the RF prime corresponding filters. After guessing the KF star involved case, remain, and the annual difference is RF star. The same goes for the EB part in the opposite direction. So we can get a set of quartets. Next, we can extract the other key information using the obtained quartets. With the aid of the automated search tools, we can select appropriate parameters KB prime, KF prime to obtain the optimal time complexity. For BDMA, it's seen as a meeting in the middle way of performing the key recovery part associated with the differential distinguisher. As shown in this framework, it allows to guess all key information involved in the EB and EF parts respectively, and compute the corresponding plain text P tilde and the cipher text C tilde. Then we match the C tilde and the C hat. The C hat equals EP tilde, and to get a set of pairs. Next, we do the exhaustive search using the obtained pairs. The attack is more efficient when the key size of the cipher is bigger than the state size. For example, AES 256. We can observe GCRA allows to guess some key bits in advance and adopt the flexible key guessing strategy. BDMA allows to employ a fixed key guessing strategy based on the characteristics of the two attacks. We proposed our questions. Firstly, can guessing some key bits in advance affect the time complexity of the differential attack? Secondly, can BDMA be generalized to support any key guessing strategy? Thirdly, can the meeting in the middle technique be integrated into GCRA? Our answers are yes. We proposed the 3 generic key recovery attacks: the generic classical differential attack, the generic differential meeting in the middle attack, and the generic rectangle meeting in the middle attack, namely GCDA, GDMA, and GRMA, respectively. Before introducing GCDA, let's start with a toy example to show the effective of guessing key information in advance. Suppose the guessing 2 key bits can get 4 filters. There are 2 to the n plain text. If the attacker first generates pairs and then guesses 2 key bits, the number of pairs is shown here. The time complexity is 2 to the 2n plus 1. If the attacker first guesses 2 key bits and then generates pairs, the number of pairs is shown here. The time complexity is 2 to the n plus 2. Obviously, guessing key information in advance has a lower time complexity and reduces the number of pairs. So we integrate guessing key bits in advance into the differential attack. Our attack is based on a distinguisher with probability 2 to the minus p. The data complexity is 2 to the p plus 1. We guess a part of key information, KB prime and KF prime. For each structure, get RB prime and RF prime filters, and the number of generated pairs is shown here. Then we extract the other key information, KB star and KF star, using the obtained pairs and do the exhaustive search. The time complexity is listed in blue. Then we proposed the generic differential meeting in the middle attack, which is combined the meeting in the middle technique with the flexible key guessing strategy. For each structure, in the EB part, we get a part of key information KB prime get RB prime filters, and the number of generated pairs is shown here. In the EF part, we get a part of key information KF prime, get RF prime filters, and generate the corresponding pairs. Next, we match pairs generated in the EB and EF parts and get a set of pairs shown here. Then we utilize the remaining pairs to recover the other key information. Finally, process the exhaustive search. The time complexity is listed in blue. Further, can we combine the meeting in the middle technique with the rectangle attack? Yes, we propose the generic rectangle meeting in the middle attack, namely GRMA, like BDMA. GRMA is usually more effective when the ratio K over N is large, which is the inherent limitation of the differential meeting in the middle attack. Similar to GDMA, we get KB prime and KF prime and get RB prime, RF prime filters respectively, and generate a set of quartets. Use the obtained quartets to extract the other key information. Then we apply it to attack the scanning EV2 and achieved a first 38-round rectangle attack, which is one more round than the previous attack. Now we simply compare the time complexities of BDMA, GDMA, and GCDA to show their effects. First, BDMA versus GDMA, let KF prime equals KF, KB prime equals KB. GDMA turns out to be almost identical to BDMA. The time complexity are exactly the same. GDMA can be seen as a generalization of BDMA. Secondly, GCDA versus GDMA. According to this table, if the same key guessing strategy is used, GDMA and GCDA share the same time complexity parts, T0, T3, and T4. For T1, if T1 is dominant, GDMA outperforms GCDA because using GDMA, the time complexity of partial encryption and decryption is lower. For T2, if these conditions are satisfied, GDMA will not be worse than GCDA. When the overall time balance, if the exhaustive, the counting method can be used to select the most likely candidates to test. The holistic key guessing strategy can balance T1 and T2. If T3 is large due to a large epsilon, pre-computed tables may help to reduce epsilon. To more directly so the effects of 3 attacks, we apply them to Catan 32 from 94 to 137 rounds. As shown in this figure, GDMA always performs better than GCDA on Catan 32. From 94 rounds to 97 rounds, both GCDA and GDMA have a better performance than BDMA because the last part of BDMA's time complexity is dominant, where GCDA and GDMA can use the counting method to reduce it. From 92 to 113 rounds. 21 dominance. GCDA is worse than BDMA and GDMA when KB union KF is not for K space. GDMA outperforms BDMA when KB union KF reaches 4K space. The time complexities of BDMA and GDMA are the same. From 114 to 137 rounds, the first term T1 of BDMA and GDMA turn to dominant term. GDMA has a lower time complexity than BDMA because the K-guessing strategy of BDMA is fixed, and GDMA adopts the flexible K-guessing strategy. Then we apply them to attack 12 rounds AES to 56 and 13 rounds AES to 56, which are based on a 9-round distinguisher with probability 2 to the minus 86. To verify the input difference of the differential, it involves 120 k bits. Similarly, to verify the output difference of the differential, it requires 64 k bits. So the time complexity of BDMA is 2 to the 206. Using GCDA and GDMA, we get a part of K information and get the corresponding filters is shown in blue. Using them, we can reduce time complexities by factor of 2 to the 61 and 2 to the 62. For 13 rounds, AES to 56, we add one more round to the end. In this case, KB remains the same as that of the 12-round attack, where KF becomes large. KF involves 224 k bits. BDMA fails due to a larger KF. Again, the flexible K-guessing strategy shows its advantage. Using GCDA, the time complexity is 2 to the 40. Besides, we improve the differential attacks on Catan 30 from 115 rounds to 151 rounds. For skinny EV2, we achieved the first 38 rectangle attack using GRMA. Finally, I will give a summary of our work. We proposed the 3 generic K recovery attacks. We introduced the K-guessing strategy from the rectangle attack to the differential attack. Further, upon the technique used in GDMA, we combine the meeting in the middle technique with the rectangle attack and propose the GRMA in return. For applications, we obtained a series of improved results. That's all about my presentation. Thank you.
Thank you very much for the talk. Is there any question? So what is your final recommendation with all the techniques you propose? So we should try all of them, or should we always start by a precise one?
Oh, sorry. Due to my poor English, we can communicate by email.
Sorry? I did not understand. We can communicate by what?
Email.
Okay. No. Okay, I think it's okay. We can stop here if you want.
Sorry.
Okay, thank you for the talk. So this is the end of the session.